Yeah, hello everyone. Today we are building Voxel Mesher because I got a lot of requests on how to actually mesh an object with voxels. It's a bit similar that we already did in another tutorial where we voxelized everything, and now we doing with kind of the same procedure. We will build an voxel mesh, and then we are build an vertex color for this mesh, because a lot of Octane users said they can't render the object color, so we build a vertex color, so you can render it also in Octane. And because we are building a mesher, we are doing at the end a little grow solver experiment. This is more a little experiment how to build a grow solver. It's not super performant, but we use the new points modifier for this, so you can see how to use this new node. I think we can start with some explanations. Okay, let's dive into Cinema. Okay, let me explain how we achieve this voxel mesher. So when we think of here as a 2D representation of a 3D voxel object, so we think of those squares are the voxels. So we check every polygon of every voxel, maybe for this square here, we check this one, this one, this one, and this one, and then we check if there is also from another voxel, there is also the polygon center also at a same spot. So when you think of here this rectangle, we see, okay, this polygon is at the same position as the polygon from this square. So we say, okay, we don't want those two polygons, and when we kill those polygons, at the end we just have the polygons that they have no neighbors, so not a polygon at the same spot. So this will be like the outline here, like this, and when we have all those polygons, we connect them together, and then we have a voxel mesh, and that's the whole procedure. So I think we can jump into nodes and have a look how this works. Okay, what we need first is an nodes capsule. So we use an object group capsule here. Open it. So let's make some space here. Okay. So what we need first is, of course, an object that we like to voxelize. So let's go to the content browser, search for pineapple. Let's take the pineapple here. And then add the pineapple here to the node setup. And here we have the geometry of the pineapple. Let's zoom in here. Here is our pineapple, and now we like to voxelize the pineapple. So as in the other tutorial, we can do this with a volume voxel fill distribution node. So plug this in here. Then we have here the distribution. It's an array with all the information. So we have to iterate over this array. And then here we have all the positions of our voxels. But first we have to decide how big are our voxels. So we have here the voxel size of 5 and interior filter of 100%. That's fine for the moment. So let's build a cube. Oops. Cube. And then the size of the cube should be the same size as we have here in the voxel size. So let's make a parameter here out of the voxel size, and also add this here to the size. So our cube has the same size as our voxel size here. And then we have to clone those cubes onto the positions here of our voxel distribution. So we can do this with a transform geometry. So add the cube to here, and then we could use select the matrix here. And now we have to collect all the cubes inside of an array to close here this iteration. So we use an assembly collection. Then what type we want to collect is a geometry object, so our cubes. And this should be inside of an array. Then we can close here the iteration, and all our cubes go here into this array. And then we use an connect object to connect all those cubes into a single geometry. Let's say connect, add this here to the geometry, and this to the output. And I think our pineapple is very small, so we have to adjust this. Maybe let's check how big the pineapple is. I think the pineapple, it's around 20 to 30 centimeters. I think there is a little bug here with the input here. So the cubes are still too big and that the input don't appear. So let's build our own input here. You can right click here and say add an input. We like to add a float and then say again 5 centimeters. Add this here to the voxel size and also to the cube. Then delete this input, and now I think it's a bit too big still, so maybe say like 2 centimeters or maybe 1.5 here for testing. Yeah, and then we see here our pineapple is voxelized. So let's hide the pineapple here. The next step, we like to have here all our polygon information. So for every polygon we need the center and every point for the polygon, as I explained here. So let's build a container where we have this information. So first we need the polygon information. There is a node called polygon info. And here we have the information that we need. We have the centers and also the positions, the point positions of every polygon. And now we like to build a container. So let's say compose container. And in this container here we like to have an array collection, and inside this collection we need the points here, the points array and the center array. So here let's say centers, oops, we need just a lowercase center, and the centers are vectors, so replace this with vectors. And then also the points, and the points here, when we click on the points, we see it's an array with an array inside with vectors. So let's rebuild this. We say here positions, and the positions is an array, and inside of the array are the vectors, so the point positions. So replace it here with a vector. Then add the centers here to the center and the positions here to the positions. Maybe let's call them centers and positions. Whoops, we have to reconnect them. And now we have to find a solution how to check all the polygon centers if they're in the same spot or not. We can do this by sorting our container first by the centers. So we can use a sort collection for this. Then let's sort the collection, and we say we sort it by the centers. That means that we sort the container by the X, Y, and Z component of the center array. So polygons with the same center will be straight after each other in the order of the array. Let me show this. We have to output this first. We can use a text here for debugging. So let's plug here our collection here to the spline, and then let's output this. We have to wait a bit. Okay, then let's open the data inspector here. Oops, sorry, not here. Here, data inspector. Okay, and now here we have all the centers, and now you see the centers are sorted here by X, Y, and Z. So when we maybe go here into the center, and now we see here we have two centers that are at the same spot, and also here this one not. So we see, okay, these two polygons are inside of the mesh, so we have to delete them, and this one looks like this is a polygon like on the surface of the mesh, so we have to keep them. And how can we achieve this? Is like we checking every position here, and we have to check is the previous at the same spot, or is the next at the same spot. We see for this one the center is not at the same spot as the previous and the next center. When we maybe check this one, we check, okay, is the previous one? No, it's not at the same position, but the next one is at the same position, so we don't need this. And also for this one, we check, is the previous one at the same position? We see, yes, it is at the same position, so we also don't need this. So we delete this one, and we keep this one, we delete this, and so on. Okay, let's bring here our geometry back. Oops. And now let's iterate here over our collection. And now here we see we have all the centers and all the positions. And now we need for every center, we need the previous center and the next center. So first, let's use get member here to get just the centers from our collection. Type in center. Now we have here an array with our centers. So, and then let's say get element. Then we need the previous one. So this is the index -1. So use a subtract. So from the index, subtract 1. And this here is our previous center. And let's do the same for the next. So just here, instead of subtracting, we add 1. And now we have here the previous center for the current center and the next center. And now let's compare those centers, the previous and the next, with the current center. So we use a compare. So we like to compare vectors. So we say if they are not equal, so that means if they're not equal, then we have a polygon at the surface. So then we have here a result of true. So let's compare both. And then if both are true, that means this is a polygon on the surface. So let's use a Boolean operator to check the operation AND. If this and this is true, we like to keep our centers and also our points. So we have to collect those inside a container. So we can use an append node for this. Append elements, and then the data type, that's the same as our composed container here. Oops. And with the append here, we can decide with the count if we like to add the center and the points or not. So then here our result goes into the count, and actually we don't need the centers anymore. We can just collect the positions here of each polygon, and now we have here a new array collection with all the point positions of each polygon on the surface. So, and in the next step, now we have here an array with the our desired positions here for every polygon on the surface. Now we have to rebuild the topology. So make some space here, then iterate over the collection again. Iterate over the collection here, and here are our positions. And with the node geometry property set, with this one we can build our new geometry, and for this we have to define the topology. So you can use a topology set. It's here, polygon topology set, and this goes into the topology. Here we need to define the point indices and also the outlines. Outline means how many points each polygon has. So, and also then here we can feed in all our points. So let's start here with the points. First we need all the positions here of our individual polygons. So let's iterate over the positions, and then we append all the positions of each polygon inside a single array. So we use an append element, and this is vectors inside of an array. And now we have every point inside a huge single array. So these are all our points here. And now we need an array with all the point indices. So that's from 0 to the count of all the points we have here. So we can build this with a range. And here we start by 0, and the end will be the count here of our polygons times 4, because every polygon has 4 points. So we use a multiply. So the count multiply by 4. And then we have here a range from 0 to the count of all our points. Let's assemble those. Sample collection, and we like to collect integers, so the indices of our points inside of an array. Maybe switch the multiply to integers, and This will go into our points here. And now we have to define the outlines. So the outlines is we have the amount of polygons, and every polygon has like 4 points. So we can do this with a fill array, and then the length is the count here of all our polygons, and the fill value is integer, and then we say, okay, 4 points. So every polygon has 4 points. We add this here to the outline. And now fingers crossed, let's output the geometry. So something went wrong, let me check. Okay, you have to set this iterate collection here to independent pass. And of course here the assembly collection here, because we collect all the integers, all the indices, and we have to switch it also here to integers. And now let's check our geometry by flying into it. Yeah, and we can see here, yes, it's now hollow geometry. So everything worked. Okay, in the next step, we like to transfer the color here of the pineapple to the polygons, to a polygon vertex color of our voxels, of our voxel mesh here. So first, let's connect the polygons first. So we can do this with a optimize. Now all the polygons, all the points are connected now. So it's, you see here with a tolerance of 0.001. So let's check this. Now we see, yeah, all the polygons are connected. And then we have to bring the texture here of the pineapple into a vertex map. So we can parse the vertex map, the vertex color here. So let's add an vertex color, vertex color tag. And then say, let's use transfer, delete this one. And we use a shader field, and inside the shader field you can say use the color of this material here. Let's check the material. It's not inside the color channel, so here it's inside the reflectance, the texture. So let's go here to diffuse, and let's bring this here to the color. Maybe hide this. Let's check. And yes, this worked. So maybe deactivate this and check. Yes, and now we have the texture here as a vertex map on our pineapple geometry. Then let's bring in this vertex color information. So we can use get geometry property get, and then we like to have the color, and our pineapple object is here. So use this one. Then the name is vertex color. Let's check. Yes, that's okay here. And what we have to do now here is run over every polygon center and check and search the closest point of the pineapple, and then we get the vertex color from this point, and we add this to the vertex color of our polygons. So let's grab the polygon information again. Polygon info. Here we have the centers of our polygons. So let's iterate over the polygon centers. And then let's use the closest points. So we like to check the geometry of our pineapple here and search the closest point. Then here, bring here to the query position the polygon center. Then let's get the indice here. So here's the nearest indice. Here on the closest point, we check the distance by 100 centimeter, and the nearest maximum neighbor is just 1. That's enough. And then let's get the corresponding color here from our geometry property get. So let's get the corresponding color from the nearest indice. And now let's collect this color, because every polygon has 4 points. We need this color 4 times. So let's use an append element. Then we like to append color inside of an array. Let's switch it here to color, sorry. And because we need the color 4 times, so for every point on each polygon, let's type here the count of 4, put this in here, and now we have the corresponding color from the pineapple vertex map 4 times inside here. So for every point we have the same color. And now let's set the vertex color for our voxel mesh. We use a set geometry property set. We like to set the color, and we add this to here, and of course we like to set it here for our voxel mesh. And now when we output this, you will see we get something different here. Let's check this. You see, this don't looks right. That's because we have to tell here the geometry property set that this is a polygon topology where we like to set the vertex color. So we have to do something similar that we did here, where we built the actual geometry. So we use also a polygon topology set. So we have to define the topology. So first we also have to decide the indices. So let's do the same trick with the range node. Let's use a range node. Then we build an iteration from 0 to the count of all our colors here. So use a get count. So get here the amount of all our colors and the count here to the end. Let's assemble this. Sample collection. So we like to have integers, so the indices of all our points, and this inside of an array. And this goes to our point indices here. And then the same with the outlines. So let's get the count here of all our polygons. So we can use here, for example, the centers. So this is the amount of all our polygons. Then also an fill array again. Fill array. say, okay, every polygon has 4 points. Oops, that's the length, sorry. The length is here the count, and then the fill value is integers and 4 points for every polygon. And this goes here to the outlines, and then this back here to the output. Now we can see here we have a polygon vertex color, not a point vertex color. As you see here are circles and here are rectangles. And now let's check. And now let's hide the pineapple. We can see we transferred successfully the vertex color from our pineapple to the polygon vertex color of our voxel mesh here. So, and this vertex color you can use, I think, in any render engine, also in Octane. Now in this last step, so this is kind of an additional part, because we have here kind of a mesher. We can maybe also, let me show, we can smooth the geometry. Smooth geometry. Maybe like just one iteration. And then we see we have here kind of a remesher. So maybe let's change the voxel size here. Yeah, you can see it acts as kind of a remesher. And this remesher now we can use inside of a memory solver to build kind of a growth solver. This is more like an experimental thing, but we can use the new points modifier. So let's start to build this. Let's make here a duplicate. So let's say here this is the solver and this is for the color transfer, because we do the solver without the color transferring. So we have this here as a backup. Let's jump into this one and let's delete the whole color part here and just do the smoothing. Because we like to do this step by step inside of a solver, we have to bring everything into a memory node. So let's collect everything. Here is the initial geometry and here is our final remesh geometry. So let's collect everything here and then go to create, and let's group this as a memory node. Let's bring this a bit together here. And what we like here, the initial type here is the initial geometry. We have to switch this to geometry object, then switch here geometry here to the initial geometry, and then this here to the next output here. So maybe let's call this geo. We don't need those anymore. Let's jump in. Let's reconnect them also here and here. Let's delete those inputs here. And now we have here our mesh back, and now we are inside of a solver, so we can manipulate here the object over time. And what we like to do is we like to, depending on the noise, we like to push the mesh along the normals and do this step by step and always remeshing the whole object again on each frame. So let's build this displays along normal part. For this, first we need some point normals. Let's generate point normals, and then we use the new point modifier. This one, points modifier. Then plug in our geometry, and you can see here we have a folder icon, so that means we can jump into this point modifier. And now we here, inside here, we iterate over all the points, and we see we have all the geometry information that we can manipulate inside here. Okay, first we need noise. So sample noise. Put in here the position. I think this is way too big. Let's go small here. And then we maybe also like to ramp the noise with a spline mapper. Oh. Where is it? Spline mapper. Yes. So we adjust here the noise value here, something like this. So we can always readjust this, and then we like to have kind of also a strength, so an amplitude of the noise. So this we can use with a simple multiply. So let's multiply the noise maybe by 3. And then maybe let's make some outputs here for the spline and also here for the multiply. Maybe say strength, displacement strength. And now we like to scale our normals corresponding to our strength here. Let's use a scale for this. Like to scale a vector, so our normal. And then this manipulated normal, so the scaled normals, we like to add to our point position. So let's take the position and add the manipulated normal. And this goes back here to the position output. Then let's jump outside here of the points modifier. Plug it to here. You can see there's already a displacement going. I think it's way too strong. Let's try 1. And let's check. I think the noise is also a bit too large. So maybe jump into the points modifier. Also use here the scale, the noise type, and the seed. Make some inputs. So we can here on the points modifier, we can adjust here our displacement. So let's tinker around, maybe use wheel noise, then the scale maybe 0.05 or maybe to 2. Let's check. Yeah. Maybe to the other side. Side is a bit smaller. Let's check. Yeah. And you can see now we have kind of a crossover. Of course, it's not the fastest solution, but because we built kind of a remesher, this is something you can do. Maybe in the future we have a fast remesher inside Nodes, and this is the typical procedure how to build this kind of displacement solver. So yeah, that's it for this tutorial. It was definitely a bit an advanced one. I hope you could follow my explanations, and if you have any questions, let me know in the comments. I'm here to help. And of course, you can download the tutorial files on Gumroad, link in the description. Bye bye.